Hi! In our previous video, we went through what are power sets and Cartesian product. In today's video, we'll be continuing the journey in set theory, and now we'll talk about finite unions and intersection, which is actually a generalization of what we already have for the union of two sets. So, you have no difficulty in forming unions with three or more sets as well, because you just do it one union the other union another, and then you can group them. You just know that they are just collecting all the elements inside there. But let's write out a more precise definition of what we want to mean by collecting all the elements in every group set. So the finite union of n sets, where x, it just means you collect all the x's such that x lies in at least one of the sets from 1 to ai for I in between 1 to n, and the intersection means that the x lies in all the other sets. So intuitively, this means that the finite union consists of everything that is in at least one of the sets, and the intersection consists of everything that is in common to all of the sets. We can now define the notation, which is a big U, and then there's an index 1 to n to represent this. And this just really generalizes from the notion of the simple two-set union and two-set intersection. Some people just call this the grand union, but it's up to you. And we also can prove the similar properties of distributive and De Morgan's law, which we have already done for the two-set one. And this actually just uses induction, because you can just induct on the number n. I'll leave that to you for exercise, and we'll move on to more interesting things. So the notion can also be generalized to infinite number. Of course, in this case, you can't really use induction to prove, but you can just define it as so. So you define a new notion for the infinite case, where it just lies in at least one and the other one lies in every set. So it's the similar properties that you want to keep. So now let's take an example where A1 is minus 1, 0, 1, A2 is minus 2, 0, 2, AI is just minus I, 0, I. If we extend these i's to infinity, then you can observe when you group them all together, it will just result in the set of integers, and the intersection of all of them is just the 0. And so we can also rewrite our notation from this union index to just saying that I belongs in a set where 1, 2, or 3. Because if you expand this out, it's just A1 union A2 union A3. And in this case, it's the same. A1 union A2 union A3. And so, it can be understood as the union of the sets AI for I, 1, 2, and 3. Likewise for intersection. And if you were to do it for infinity, then your I just runs for all natural numbers. And so, we're actually taking a union of a collection of sets AI, where the I is an element of some other set, and this other set is also known as the index set or indexing set, and this I acts as a subscript for your family, so it just labels your sets in your family. So these collections of sets is just a family of sets. So a family of sets is just a set that contains many other sets. And we denote by family because they are somehow related to each other. Like in this case, minus I, 0, and I. And so we use this type of indexing set when it's useful when your original set AI is related to the index in some way or another. Then it makes the notation much simpler to remember and understand. So because it's a general indexing set, it doesn't always need to be integers. It can be real numbers, it can be anything. And thus we can just write A alpha instead to reduce the confusion where I can maybe take for integer, but it doesn't really matter as long as you're clear what you are doing. So you just need to remember that the indexing set is just a useful way to remember how the A alpha looks like, and it just serves as a possible subscript. So we can then define the grand union over an indexing set for X to lie in at least one of the sets in the family. And so this means that X is in the ambient set, in the overall space, and then there exists an element in the index such that X is an element of the one of the sets in the family labeled by that index. Similarly, the intersection will just be the elements that lie in all the sets. So you define it in so because it really works in the same way as the original union that you have already done. So with all those definitions, we also want to prove similar properties about our grand union over an index set instead. And so we want first let's just prove one of the basic ones, which is just the distributive laws of intersection. And so we want to say these two sets are equal. So we just do it by definition again. So it lies in this set if and only if it's an element of B and it lies in this grand union. To lie in the grand union, that means there exists an index such that X is an element of A alpha. Since B is nothing related to this index, you can push it all the way through. And so you can rewrite the logic, the sentence as follows. And this just means that X is an element of B intersect A alpha. And this just defines it to be the grand union over the index set. And you can see that all the distributive properties, all the commutative properties that we want to hold true in our finite case also holds true for arbitrary index set. And so this definition is very intuitive and helps reinforce the idea of what we want. So it's like saying that you make a definition so that it goes hand with hand with what you already have. Now that we have this notion of an indexing set, we can ask the question on what happens if this index set is empty. Well, if you just take the union of A alpha, where alpha is an element of the empty set, if you write out the definition, it's just collecting all the x's such that there exists an alpha in the empty set such that X is an element of A alpha. But the problem is now there exists an alpha in the empty set is a false statement. And so this whole proposition is false. And so there is no element in this set. And the only set with no elements is the empty set. So this grand union over the empty set is still a set. And it's just the empty set. So it has no elements. But if we were to look carefully in the intersection of alpha over the empty set, you're collecting all the elements that is in every A alpha. So for all alpha in the empty set, X is an element of A alpha. If we were to rewrite this, it means that for all sets, alpha is in the empty set implies that X is an element of A alpha. This is false. And so the whole implication will be a vigorously true statement. And so this is always true, means you put whatever, you take whatever set you want. It will lie in this, supposedly this set. And so this element, this mathematical object contains all sets. And the problem with naive set theory is you just say that this is a set that contains all sets. But there is actually no set that contains all sets. And this is known as Russell's paradox. And that is the whole reason why naive set theory leads to paradoxes and contradictions at times. And the need for axiomatic set theory comes into play. I won't dive very deep into axiomatic set theory, but I'll just tell you using this example that it is a very important part to have a consistent theory in mathematics. Because I want to say that this is a set, but it contains all other sets, and so this can't be a set, because there is no set of all sets. So, let's take a look at what is Russell's paradox, which played an important role in building the foundations for mathematics in set theory. So Russell's paradox is a very nice slogan that says there is no set of all sets. So the proof follows that if X is a set, let's say X is the set, and this with the properties that it contains all elements in the whole mathematical world, so it contains all sets in the world. That means for every set, Y is an element of X. Then we can use the set builder, and we are able to chop down and choose those sets in this X such that it is not an element of itself. So it's just Y is not an element of Y. So for example, if you have B equals to this, well, clearly this is in this, because clearly this B is an element of B, and so this is not in this. We'll look at that later on, but just know that this has something theoretically if it was the set of all sets. But you can just ask whether A is an element of A. That means whether this set is an element of itself. If it was an element of itself, it means it must be able to fulfill this property. But this property just states that it is not an element of itself, and so there's a contradiction. Similarly, if it's not an element of this set, then it has the property that it is an element of itself. So if A is no longer an element of A in this set, then A, where the property that it contradicts this, means it is an element of A. Again, another contradiction. And so in any case, you are unable to create this set. And so the original hypothesis that X is the set of all sets cannot exist, because it will lead to contradiction. And so we also like to note that this set B equals to this, you don't even know what B is, and you say it is this. And so this is also somewhat of a paradox, and actually the axioms of set theory states that cannot happen, that B equals to this recursively defined B is no longer a set. Hence, the need for axiomatic set theory is to remove such inconsistencies in our theory of mathematics. Hope you have enjoyed this proposition of Russell's paradox, and hope you have enjoyed this short tutorial on set theory. I'll be moving on to functions in the next video, so stay tuned. Thank you.